You've seen the videos, a massive printer head, like a high-tech cake icing nozzle, gliding back and forth, magically extruding the walls of a house in a single day. The promise is revolutionary, affordable, fast, waste-free, and architecturally daring homes. Printed on demand, but is this the future of construction for everyone? Or a niche solution for specific problems? The truth is fascinating and more complex than the headline suggests. 3D construction printing, or additive manufacturing for buildings, is a real and rapidly advancing field. But it's not about replacing every bricklayer tomorrow. It's about redefining what's possible in form, efficiency, and access to shelter. Let's look at how it actually works and where it truly shines. First, the technology. There are two primary systems. The first is the large-scale gantry system, like a giant XYZ plotter that frames the entire building footprint. This is what you often see printing small homes on site. It's stable and precise but requires significant setup and a clear, level sight. The second, more flexible method is the robotic arm. This industrial robot, often mounted on a track, can print more complex, non-rectilinear shapes and can be used in a factory setting for prefabrication. Both systems share the same core process. They take a digital 3D model, slice it into layers, and translate that into a toolpath for the print head. This head extrudes a specially formulated material, almost always a cementitious mix, layer by layer. A pro tip from material scientists: the ink is critical. It's not standard concrete. It must have the right viscosity to hold its shape immediately after extrusion, a property called buildability, yet still bonds seamlessly to the previous layer. It often uses additives like fibers for reinforcement and accelerators for quick setting. The goal is to print continuously, without needing formwork. This leads to the key advantages. The number one benefit is the elimination of most formwork. Formwork is one of the most labor-intensive, material wasteful, and costly parts of concrete construction. Printing needs almost none. Second is design freedom for complex geometries, curved, organic, and structurally optimized walls that would be prohibitively expensive with traditional formwork can be provided for essentially the same cost as straight walls. Third is speed. Once the printer is set up, wall printing is incredibly fast, reducing on-site labor time dramatically. This makes the technology incredibly compelling for disaster relief, rapidly printing durable basic shelter cores, and for affordable housing projects where repetitive units can be printed efficiently. However, the limitations are just as important to understand. We are currently printing walls only. The roof, floors, windows, mechanical, electrical, plumbing, and finishes are all still installed by traditional means. The printer creates a monolithic concrete shell, which presents challenges for insulation and reinforcement. The current solutions are either printing double walls with a cavity for insulation and rebar, or using a steel or rebar mesh as the print progresses. Then there is the regulatory hurdle. Building codes are written for conventional systems. Getting approval for a load-bearing printed concrete wall requires extensive testing and pioneering work with local authorities. And finally, cost. While it saves on formwork and labor, the capital cost of the printer, the specialized material, and the engineering expertise is still high. It's not yet cheaper than a stick-framed house in many markets. So, the real impact today is in specialized applications, bespoke architectural features, affordable housing prototypes, emergency shelters, and military applications. It's a tool of incredible potential, not a magic wand. It forces us to reimagine buildings not as assemblies of thousands of parts, but as digitally crafted, monolithic organisms.